once again, and we go on to the second part of today's lecture on applied respiratory physiology. In the earlier part of the evening, we had spent about 45 minutes covering 7 of the 9 subtopics that I had wanted to cover as part of the first segment of my lecture on applied respiratory physiology. And those components that we covered included tidal volume, functional residual capacity, closing capacity, atelectasis, compliance, airway resistance, ventilation perfusion, and its distribution. And that left 2 more topics for us to complete. And that's what I will do before we go on to the later part of today's presentation. We left off here this evening, just before the break, and we were to talk about the peak expiratory flow rate. Now, the peak expiratory flow rate, as the name itself signifies, is the maximum rate at which air flows out of the lungs during expiration. And in women, the normal value is around 350 to 500 liters per minute, whereas in men, it's 450 to 600 liters per minute. Now, what is the importance for us to know about the peak expiratory flow rate? Peak expiratory flow rate obviously decreases when there is any airway obstruction. It could be due to a tumor. It could be due to secretions in the tracheobronchial tree. It could be due to bronchospasm. But whatever the reason, the peak expiratory flow rate comes down when there is any element of airway obstruction. And what this does to the person's ability to breathe is the ability to inhale maximally and exhale forcibly is compromised. And as a result of this low peak expiratory flow rate, the person's ability to cough and clear secretions, particularly in the post-operative period, comes down. And this is believed to be one of the reasons why patients develop pulmonary complications in the post-operative period. So we'll just examine the 4 steps that are involved in a cough. And when there is an irritation in the tracheobronchial tree, it could be some phlegm in the tracheobronchial tree. It could be a small foreign body that has entered, like a food particle or whatever, that causes irritation of the tracheobronchial tree. And that is the first part of the 4-component cough reflex. And immediately after this, what happens is the person takes a deep inspiration. And therefore, to have an adequate cough reflex, one has to have the ability to first sense some irritation in the tracheobronchial tree. And immediately following that, the person has to have the ability to take a deep inspiration, which is essentially a vital capacity maneuver. And this fills up the lung volume. And soon after this, in the 3rd phase of the cough reflex, you find that the person exhales forcibly, but exhales against a forced and a closed glottis. As you can see, these 2 arrows here, the glottis is closed. And in the subglottic region, very large amounts of pressure are developed. You can see these multiple arrows trying to push against the closed glottis during the period of what is called the compression phase of the cough reflex. And eventually, when the glottis opens out, the force that has been generated, the pressure that has been generated in the subglottic region is now suddenly released. And this is what results in the peak expiratory flow rate of what we mentioned of 350 to 500 liters per minute in women and 450 to 600 liters per minute in men. And this results in expulsion of the foreign body or expulsion of the phlegm or whatever is there within the tracheobronchial tree. And thereby, the pulmonary toileting gets complete and reduces the possibility of postoperative pulmonary complications. Now, very often when we ask residents the question, what is peak inspiratory flow rate? Most residents are very familiar with the earlier term, peak expiratory flow rate, but there are several times when residents confuse peak inspiratory flow rate to peak expiratory flow rate. And therefore, I thought I will include this also as part of our discussion. So the peak inspiratory flow rate is the maximum rate at which air flows into the lungs during inspiration. And this has a normal value of 35 to 50 liters per minute. Now, once again, let us imagine that a person is taking a tidal volume breath of 500 ml or half a liter, and this Let us imagine that the person takes it within 1 second. The rate of flow of gases into the lungs would be 0.5 liters in 1 second, or 1 liter in 2 seconds. Or if you were to extrapolate this to 1 minute, it would be 30 liters per minute. So when we take a half liter or a 500 ml tidal volume in 1 second, what essentially we are doing is we are taking in a peak inspiratory flow rate of around 30 liters per minute. So generally, the peak inspiratory flow rate in most adult healthy individuals is around 35 to 50 liters per minute. And what is the importance of knowing this? The implications of knowing the peak inspiratory flow rate is one of two. Coming to the anesthesia breathing circuits, we know that the anesthesia breathing circuit has a reservoir bag, and the function of the reservoir bag is to collect fresh gases during expiration and the expiratory pause. So during inspiration, whatever gases come into the anesthetic breathing circuit can be breathed into the lungs of the patient. But during expiration and expiratory pause, the reservoir bag, which is part of the breathing system, now collects the fresh gases and is ready to deliver this during the next inspiration. And it is this reservoir bag that provides the peak inspiratory flow rate that is required for a patient from an anesthetic breathing circuit. So the function of the reservoir bag is therefore to provide the peak inspiratory flow rate. The other application or implication of knowing the peak inspiratory flow rate is when we talk about oxygen therapy devices. And we've all heard of the device called the Venturi device, which is one of the examples of a fixed performance device. It's called a fixed performance device because irrespective of the age of the patient or the breathing pattern of the patient, this device provides a reasonably fixed amount of FiO2. And at the bottom part of this figure, you find several nozzles that are provided from 24%, 28, all the way down to 40%. And in the middle diagram and in the top diagram here, you can see a jet orifice and an air entrainment port. So when oxygen is flown in through the jet orifice and this air entrainment port is open to different extents, different amounts of air are entrained through this air entrainment port, and this dilutes the oxygen in such a way that the total flow of oxygen plus the air that is entrained will now exceed the peak inspiratory flow rate of the patient. And this is how the Venturi device becomes more or less a fixed performance device. It's the closest we can get to the simple, commonly available oxygen therapy devices that gets close to being a fixed performance device. So this completes actually the part one of applied respiratory physiology. So what we talked about in the first maybe 45 to 50 minutes is the importance of volumes and capacities. And we emphasized the importance of tidal volume and vital capacity in as much as it is required for us not only to set the tidal volume on anesthetic ventilators and ICU ventilators, but we also emphasize the importance of our knowing the normal values for tidal volume and vital capacity when we talk about initiation of ventilatory support and weaning off ventilatory support. We talked about functional residual capacity as a buffer within the lung, which provides the oxygen reserve for the blood flow through the pulmonary circulation to pick up oxygen. And we said that the FRC is best in the sitting position, it comes down in supine, and it gets even worse with the induction of anesthesia. So we also talked about the relationship between functional residual capacity, closing capacity, and residual volume. And we said that when the closing capacity increases in certain situations, it predisposes to atelectasis. And we talked about two of the mechanisms by which we can overcome this atelectasis, which was a psi mechanism, the use of PEEP, and the use of recruitment maneuvers. We defined compliance and airway resistance, and we looked at ventilation perfusion ratio and how it affects gas absorption at the level of the alveoli. And finally, we looked at the two flow rates, the peak expiratory flow rate, which is very important in order to, for the patient in the post-operative period to have an adequate cough reflex. And we looked at the peak inspiratory flow rate as an important factor that determines how the anesthetic breathing circuits work and how Venturi devices, which are fixed performance or closest that we can get to fixed performance oxygen therapy devices, work. Right. So now I shall go on to part two of applied respiratory physiology. And in this section, I'm going to talk about the physiology of oxygen transport. Now, all that we spoke about until now in the last 50 to 55 minutes was geared at how uh, fresh atmospheric gases was drawn into the lungs, into the alveoli for the oxygen to be taken up by the pulmonary blood flow, and how the carbon dioxide excreted into the alveoli was eventually excreted from the alveoli through the tracheobronchial tree into the atmosphere. So now we will look at how oxygen transport happens from the atmosphere right down to the tissues or the cells within the body. So as an introductory sentence, I would like to say that we breathe to take in oxygen that sustains life, and also to remove carbon dioxide, which is the end product of cellular metabolism. This is the very reason why we breathe, and it's a very simplistic way of looking at why we breathe. Now, we also need to remember that in physics, all gases and liquids are referred to as fluids, and fluids, which implies gases as well as liquids, always move down a pressure gradient or a concentration gradient. So you never find gases or liquids going against a pressure gradient. They always move down a pressure gradient, and obviously it's like saying that you never see a waterfall flowing upwards. Waterfalls are always falling downwards. And I just thought I'll break the monotony of applied respiratory physiology by placing this beautiful photograph of the Dudhsagar Waterfalls, which is in Goa. What you can see on this slide is the Konkan railway track. And in the early days of the Konkan railway, in fact, the engine driver used to be very considerate. He used to stop the train on top of this bridge for everybody to get off the train and take a good view. It was almost like a photo spot in the early days of the Konkan railway, and it's a beautiful spot, especially in the monsoon. And the reason I mention this is because I just want to emphasize the fact that gases and liquids always flow down a pressure or concentration gradient. Now, if you have to review how oxygen is transported from the atmosphere to the tissue cells, we need to break this up into several processes, because the steps of transfer of oxygen from the atmosphere right down to the tissue cell takes place in a number of steps, which includes what is called the oxygen cascade. Like you see here in this diagram, this is a water fountain that we normally find inside houses, and you have a circulation of water. It falls from the first tank here into the second to the third, and it's pumped up again here, and it keeps on continuing in a form of a cascade. So again, oxygen cascade is nothing but the various steps. Those are the pressure or tension gradients down which oxygen moves from one phase to another. Now we shall first examine how atmospheric air reaches the alveoli. Now, room air has 21% oxygen, and if you were to take the atmospheric pressure at sea level to be 760 millimeters of mercury, and 21% to be contributed by oxygen, the partial pressure of oxygen in dry air at sea level would be 760 millimeters of mercury multiplied by 0.21, which gives us a value of 160 millimeters of mercury. And this is what is creating the starting point of what we call the oxygen cascade. Along the y-axis, we have the oxygen tension, and the first step starts a little above 150 millimeters of mercury, which is 160 millimeters of mercury, which is the partial pressure of the gases in the dry atmospheric air, and that is where the oxygen cascade or the waterfall starts. Now, when we breathe these dry atmospheric gases into our lungs, our body does two things to this. One, it humidifies the gases, and two, it warms up these gases to our body temperature of 37 degrees Celsius. Now, at body temperature of 37 degrees Celsius, water vapor, when it's fully saturated, exerts a partial pressure of 47 millimeters of mercury, and that needs to be subtracted from 760 millimeters of mercury when we now compute what is the oxygen partial pressure in humidified and warmed air as it is approaching the alveoli. So this is computed by this equation, 760 minus 47, which is the saturated vapor pressure of water at body temperature of 37 degrees Celsius. That gives us a value of 713, 713. And when this is multiplied by a factor of 0.21, we get a value of 150 millimeters of mercury, which is what forms the first step from the starting point of 160 millimeter mercury. The first step that is created is because of the humidification and warming up of inspired gases as it travels down the tracheobronchial tree. And this step results in the oxygen tension in the gases reaching the alveoli to reach a value of 150 millimeters of mercury from the starting point of 160 millimeters of mercury. Now, in the alveoli, we know that carbon dioxide is continuously getting excreted into the alveoli because of the difference or the concentration gradient that exists between the pulmonary arterial deoxygenated blood and the alveoli. And to compute what happens to the alveolar oxygen tension at the end of this carbon dioxide exchange, we make use of what is called the alveolar air equation, which is nothing but the alveolar oxygen tension is given by the inspired oxygen tension, which we have calculated as 150 millimeters of mercury, minus the arterial carbon dioxide tension divided by the respiratory quotient. So the normal arterial carbon dioxide tension is around 40 millimeters of mercury. So 40 divided by 0.8 gives us a value of 50. 150 minus 50 gives us a value of 100 millimeters of mercury. So once the warmed and humidified gases reach the alveoli, the alveolar oxygen tension now drops from 150 millimeters of mercury to 100 millimeters of mercury, which is what you find here in this step. So in the ideal alveolar gas, you find that the capital AO2, the alveolar oxygen tension, now reaches roughly around 100 millimeters of mercury, which is the continuation of the oxygen cascade as we go from the atmosphere up to the alveoli. Now, once you have seen how these 2 or 3 steps have happened in the oxygen cascade and how the alveolar oxygen tension of 100 millimeters of mercury has been achieved, the next point that we need to look at is how this oxygen from the alveoli ultimately reaches the cells. And to understand this, we can break up this process into 4 steps. We can consider that the transport of oxygen from the alveoli to the cells takes part in 4 independent steps. So let us look at each of these steps one by one. The first step is the diffusion of oxygen from the alveoli into the pulmonary capillary blood flow, and that is depicted here in this diagram. Now, I've taken photographs or diagrams from different textbooks, so there may be a slight difference in the numbers that are depicted. So the PO2 I told you was 100, but we can take it as 104 also, the alveolar PO2, 100 or 104, because of the different source from which I've taken this particular diagram. But what this diagram shows us is in the top half, you have the pulmonary capillary. This is the alveolo-capillary membrane. The purple membrane on top is the alveolar wall, and the red vessel below is the pulmonary capillary. The left end of this capillary is the pulmonary arterial end, which carries deoxygenated blood. And the right end of this capillary is the venous end of the pulmonary vein, which carries oxygenated blood. Now, because of this, you see these arrows going back and forth. You find that at the bottom half of the diagram, when you examine that, you find that the blood PO2 from a pulmonary arterial level of 40 millimeters of mercury very rapidly builds up to about 100 to 104 millimeters of mercury by the time the blood has traversed even the first 1/3 part of the pulmonary capillary. Now, generally they say that it takes about 0.75 seconds for the blood or the RBC to travel from the arterial end of a pulmonary capillary to the venous end of the pulmonary capillary. So what it means is that in 1/3 of that time, 1/3 of 0.75 seconds or 0.25 seconds, the blood has already become completely oxygenated. And the rest of the time it just plateaus out, and we have that much of a reserve in order to take care of oxygenation should there be an issue of an increased oxygen demand, as would happen during exercise. So even during exercise, what would happen is the blood PO2 would build up maybe in a more gradual manner, but by the time the blood reaches the venous end of the pulmonary capillary, it would have got completely oxygenated. So the pressure difference of 100 or 104 millimeters of mercury in the alveolar PO2 to the venous end, the arterial end of the pulmonary artery of 40 millimeter mercury gives a gradient of approximately 60 millimeters of mercury, which is what results in this rapid equilibration of the tension of oxygen. and completely oxygenates the blood by the time it reaches the venous end of the pulmonary capillary. So this completes step one. Now, we saw this diagram in a bit more of detail in the first half of today's lecture, so I won't spend too much time on this. And all I will say is that on the basis of this, we can imagine that the alveoli, or the blood that is draining the alveoli from the apex of the lung, has a slightly different composition to that is draining from the base of the lung. And we mentioned in the earlier part of today's lecture that somewhere around the hilar region, where you have a VQ ratio of an ideal 1 VQ ratio, you get the alveolar oxygen tension of 100 millimeters of mercury and alveolar carbon dioxide tension of 40 millimeters of mercury. And this is what is in equilibrium with the blood that exits from this ideal alveolus. And the number is again similar. The pulmonary vein, that is the pulmonary venous end of the capillary, now has a tension of 100 millimeters of mercury of oxygen and a carbon dioxide tension of 40 millimeters of mercury. Now, when you look at the blood that is draining from the apex, the representative numbers are given here, and from the base, you find that the numbers are slightly different. But eventually, what reaches the left atrium is the blood that drains from all the alveoli, be it from the apex, from the middle of the lung, or from the base of the lung. So essentially, all of this gets mixed. And as a result of this mixture, you find that there is something called a physiological shunt that is happening within the lung. Part of this is contributed by the blood returning from the non-ideal alveoli. Excuse me. Now, we also know that some of the bronchial veins directly empty into the left heart circulation, and the Thebesian veins from within the heart itself also drain deoxygenated blood into the left heart. And because of these three factors, you find that a total of 2 to 5% of the cardiac output actually gets diluted with venous blood. And even though the ideal alveolar blood has a tension of 100 millimeters of mercury of oxygen and a 40 millimeter mercury tension of carbon dioxide, eventually because of the dilution of these physiological shunts, the composition changes. And as a result of this, the final PO2 blood in the left atrium is around 95 millimeters of mercury, which is what you find here in the next step. As blood has left the ideal alveolar gas, it had a composition of 100 millimeters of mercury arterial oxygen tension. But because of this physiological shunts that happen, which we just discussed, the arterial blood reaching the left atrium has a value of roughly a few millimeters of mercury below 100, and we can take it as representative of around 95 millimeters of mercury. So having done with the first step, that is diffusion of oxygen from the alveoli to the pulmonary capillary, we now need to see how this oxygen is transported in the arterial blood. Now we know that hemoglobin is that pigment in our blood that binds to oxygen, and 97% of the oxygen that is carried in the blood is actually bound to hemoglobin. If we go back to our days of physiology, we can recollect that 1 gram of hemoglobin is capable of carrying 1.34 ml of oxygen. And if we take our full hemoglobin complement to be 15 grams of hemoglobin per 100 ml of blood, multiplying 15 by 1.34, you get a value of approximately 20 ml of oxygen. So the oxygen that is carried bound to hemoglobin, which is 97% of the oxygen carriage in blood, amounts to about roughly 20 ml of oxygen attached to the hemoglobin. Now, there is another form in which oxygen is carried in the blood. If 97% is carried attached to hemoglobin, the remaining 3% is carried in the dissolved form, and that is dependent on what is called the solubility coefficient of oxygen. Each gas has a solubility coefficient, which is described in terms of so many ml per ml of blood per millimeter mercury of tension of that particular gas. So when we're talking about oxygen, we're talking about the arterial oxygen tension, which is taken to be roughly around 100 millimeters of mercury. So if you were to calculate from the solubility coefficient of oxygen of 0.000031 ml per ml of blood per millimeter mercury of arterial oxygen tension, You want to calculate that for a deciliter of blood, that is 100 ml of blood. For an arterial oxygen tension of 100 millimeters of mercury, you'll just have to move the decimal point 4 points to the right, and you'll get a value of dissolved oxygen, which is 0.31 ml per deciliter of blood. So though roughly about 20 ml of oxygen is carried in combination with hemoglobin, it's a very small amount of oxygen that is carried in the dissolved form. But this small amount of oxygen is very important because this is the medium through which tissues eventually receive oxygen from the blood. So the summary of what we talked about in the last couple of minutes is that there is approximately 20 ml of oxygen being carried by 100 ml of blood, both bound to hemoglobin and in the dissolved form at an arterial oxygen tension of 100 millimeters of mercury. Now, if you take the cardiac output to be around 5 liters per minute, and imagine that 20 ml of oxygen is there in every 100 ml of blood, 20 multiplied by 50 deciliters or 5 liters would give us a value of 1000 ml. And that is what we used to call oxygen flux in earlier days. And nowadays, the modern term is what is called D with a dot on top, O2, which means oxygen delivery to the tissues per minute. And that is to an extent of 1000 ml every minute. So by carrying 20 ml of oxygen for every 100 ml of blood, the cardiac output of 5 liters per minute actually results in delivering 1000 ml of oxygen to all the tissues put together every minute. Now the question is, do we really need this 1000 ml of oxygen? And the answer is no. The amount of oxygen we need is only 250 ml per minute. So collectively, all the tissues of the body put together extract about 250 ml of oxygen from the 1000 ml that is being supplied to all the tissues put together. And this gives us a utilization coefficient of 25%. What it means is that out of the 1000 ml that is being supplied to all the tissues put together, 25% is collectively removed by all the tissues put together, that is 250 ml. And what returns to the right atrium is about 75% of this 1000 ml, which is 750 ml, which gives us a saturation of mixed venous blood in the right atrium to be 75% and a PVO2 of 40 millimeters of mercury, which is the classic numbers that we need to remember when you talk about venous blood. The blood exiting from the left ventricle, which is fully oxygenated, is distributed to all the body tissues through the aorta and its branches. And these then go to the individual regional perfusion. And we know that the body is divided into very richly perfused organs, moderately perfused organs, and very poorly perfused organs. And this results in multiple cascades in this oxygen waterfall. Depending upon which tissue is being supplied, the gradient between the blood that is coming through that branch of the artery supplying that particular organ to the tension that is there in the tissues of that particular organ will vary, resulting in a different amount or a multiple cascade of oxygen. There's another beautiful picture of the Jog Falls from Karnataka. Those of you who have seen it would have enjoyed its splendor in the monsoon. And I chose this particular picture because the Jog Falls, those of us who've seen it, has 4 independent falls, which all come out at different levels. Now, because this was taken at the peak of the monsoon, you don't really see the different levels. But I just want to emphasize the fact that the aorta from its different branches supplies oxygen to the tissues at various levels. And this is what is shown here by the last part of the oxygen cascade, where you find where this opens out and gives you multiple cascades supplying oxygen to the various tissues. Now, we've reached now from the atmosphere through the alveoli and right down to the individual tissues. So let us see what happens in the systemic capillaries and what happens to the blood coming into the systemic capillaries and what happens to it while it enters the tissue fluid. This is a simple diagram which on the reddish or the pinkish color on the left side indicates the arterial end of a capillary that is perfusing an organ, and the purplish or bluish end shows us the venous end of the capillary. So blood that is entering the arterial end of the capillary has a tension of 95 millimeters of mercury, and the tissue tension is roughly around 40 millimeters of mercury. And on an average, the individual cells, depending upon the tissue you are considering, be it maybe the heart or the brain or the liver or the kidney, each of them has a different tissue oxygen tension level, but on an average, for our understanding, we'll take it as 23 millimeters of mercury, being the average tissue oxygen tension. So you have a gradient from the arterial end of the capillary of 95 millimeters of mercury for the oxygen to enter into the tissues, which is at 40 millimeters of mercury. And from there, it enters into the individual cells because of a gradient of 40, between 40 and 23 millimeters of mercury. So this is the final step by which oxygen enters from the from the capillaries perfusing an individual organ into the tissue spaces that are surrounding the individual cells and eventually enters the tissues. Having completed step 4, we now go to the final step, that is diffusion of oxygen from the tissue fluid into the cells. Now we said that the average oxygen tension average oxygen tension in the tissues is around 40 millimeters of mercury. And we need to remember one more value, which is what is called the Pasteur point, which is a value of 1 to 4 millimeters of mercury. And we need to remember this because this is the level of oxygen tension that is there in the mitochondria, which are the factories at which all metabolism happens. And if the value, or if the oxygen tension in the mitochondria drops to a value below 1 to 4 millimeters of mercury, then the tissue metabolism switches from aerobic to anaerobic metabolism. So you have an average oxygen tension of 40 millimeters of mercury in the tissues, that is the extracellular fluid that is surrounding all the tissue cells. From there, it enters the cell. Most cells have an average value of around 23 millimeters of mercury. Some of the cells have even lower than that, like for example, the cardiac and the brain tissues. Some have higher when the extraction is less. Eventually, all tissue cells ensure that they are not further than 50 microns away from the nearest capillary. There are several capillary networks that are lying dormant, and these tend to open up when there is an extra need for circulation in this microcirculation, and ensures that the Pasteur point is never reached. In other words, the tissues do not need to switch over to anaerobic metabolism from aerobic because of opening up of these extra channels. So in summary, I say that oxygen always diffuses along a concentration gradient from the atmosphere down to the alveoli into the blood that perfuses the various tissues, eventually all the way down to the mitochondria of the individual tissue cells. The structure of the alveolar capillary membrane is designed towards efficient transfer of oxygen and carbon dioxide in two different directions. The partial pressure of oxygen within the cells in health is always higher than the Pasteur point in order to sustain aerobic metabolism. The cardiac output ensures that 1000 ml of oxygen is delivered to the tissues per minute, what we call D.O2, against a requirement of 250 ml, and this results in a utilization coefficient of 25%. And the way oxygen is carried in blood is 97% in combination with hemoglobin and 3% in the dissolved form. And even though a very small amount is carried in the dissolved form, that is the important, functionally more important form because it creates the pressure gradient for diffusion from the blood into the various tissues. So we now come to the last and third part of applied respiratory physiology, which is talking about carbon dioxide homeostasis. Now, what are the numbers we need to remember? An average 70 kg adult produces around 200 ml of carbon dioxide per minute. We take in about 250 ml of oxygen and we breathe out about 200 ml of carbon dioxide every minute. And this results in our producing about 12 liters of carbon dioxide every hour. And we have a total body store that is the equivalent of 120 liters, or the amount of carbon dioxide is produced in about 10 hours of excretion from all the cells. Now, I have just used my prerogative to label this as the carbon dioxide cascade. There is no such term as the carbon dioxide cascade, but I thought that would be an easy way to remember, because if you have an oxygen cascade that is starting from the atmospheric air that goes all the way down to the tissue cells, you have what is called a carbon dioxide cascade that works in the reverse direction. From the mitochondria, the cell factories, it goes into the cytoplasm, from the cytoplasm into the extracellular fluid, from there into the blood that is perfusing these tissues. From the blood, eventually reaches a pulmonary circulation, from where the carbon dioxide gets excreted into the alveoli and from the alveoli, with each breath, this gets thrown out into the atmospheric air. So in the reverse direction, you have from the mitochondria through the cytoplasm, extracellular fluid, blood, alveoli, eventually the carbon dioxide reaches into the atmospheric air. Now we need to know that carbon dioxide is carried in three different forms. The three forms in which it is carried is a carbonic acid, about 8% of it. As bicarbonate, the major part of carbon dioxide is carried as bicarbonate, which is about 80%, and as carbamino compound in combination with body proteins, which is about 12%, leading to the total 100% of CO2 carriage. And the amount of carbon dioxide that is normally carried is about 45 to 55 ml of carbon dioxide per deciliter of blood. Now, looking at the first way in which it is carried, that is the carbonic acid, which amounts to about 8% of how carbon dioxide is carried. The equation we need to remember is carbon dioxide combining with water to produce carbonic acid, which is a weak acid. And this happens, the first step happens at the level of the various tissues, where carbonic acid is produced in the tissue. Now, this carbonic acid is eventually carried through the right heart into the pulmonary circulation, where the carbonic acid dissociates into carbon dioxide and water, and the carbon dioxide is then excreted into the alveoli. Now, both these equations are powered or catalyzed by an enzyme that is called the carbonic anhydrase. There are 16 isoenzymes or 16 types of carbonic anhydrase enzymes in the mammals. It is enough for us to remember that carbonic anhydrase type 2 is present in the RBCs, and that catalyzes the reaction of carbon dioxide combining with water to produce carbonic acid. And carbonic anhydrase 4, isoenzyme 4, is mainly present in the pulmonary capillaries, where it catalyzes the reverse reaction of converting carbonic acid into carbon dioxide and water. The carbon dioxide is eventually excreted into the alveoli. Now, we said that the major amount of carbon dioxide is carried as bicarbonate, and the equation we need to remember for that is carbon dioxide combines with water to again form carbonic acid, and this carbonic acid, being a weak acid, dissociates into hydrogen ions and bicarbonate, and the hydrogen ion is buffered by the various buffer systems in the body. And I'm sure Anita will talk a lot more in detail about the acid-base balance and the various body buffers that are available in the body when she comes to a session, I think on Friday, as we move along APGAP2020. So 80% of carbon dioxide is carried as bicarbonate. The bicarbonate that is there in the RBC exits into the plasma in exchange for chloride, and this is through a mechanism called the ping pong mechanism, mediated by what's called a band 3 protein present on the RBC. And this is also what we call the hamburger phenomenon, or the chloride shift, by which bicarbonate from within the RBC moves from the RBC into the plasma in exchange for chloride. So there's an exchange of bicarbonate for chloride, and this is therefore called the chloride shift. The third method by which carbon dioxide is carried in blood is in combination with various proteins through the R-NH2 moiety, or what's called the amino group. So we have plasma proteins in the plasma. So some of the carbon dioxide binds to the R-NH2 moiety to the plasma proteins. And within the RBCs, a similar attachment happens of carbon dioxide to the alpha and beta chains of the hemoglobin. So about 12% of carbon dioxide is carried in combination through the amino group to the plasma proteins and the hemoglobin through the alpha and beta chains of the hemoglobin. Now, this is what exactly happens, the fate of carbon dioxide in the blood. Looks like a very complicated diagram, so we shall now break it up into two parts. One, we shall see what happens in the plasma, and later we shall see what happens in the RBCs itself. So carbon dioxide from the tissue cell enters into the plasma as carbon dioxide. It forms a weak acid called carbonic acid, which dissociates into bicarbonate and hydrogen ion. Hydrogen ion is buffered by the plasma proteins. Bicarbonate enters from the plasma into the tissue fluids, and we can also see a similar thing happening in the RBCs. Some of the carbon dioxide through the R-NH2 moiety is carried as a carb amino compound in attachment to the plasma proteins. So this is the fate of carbon dioxide in the plasma. Let's see what happens to the carbon dioxide in the RBCs. The big yellow circle here indicates the RBC. Carbon dioxide enters the RBC. Again, carbonic acid is produced. Carbonic acid breaks up into hydrogen ion and bicarbonate. Through the band 3 protein located on the surface of the RBC, bicarbonate exits into the plasma, and in exchange, chloride enters into the RBC in what we call the hamburger phenomenon or the chloride shift. Once again, carbon dioxide is directly carried in attachment to the alpha and beta moieties of the hemoglobin as a carb-amino compound. So a similar thing happens within the RBC, three different fates of carbon dioxide in the RBC. Now this diagram here summarizes for us the carbon dioxide homeostasis. All the carbon dioxide produced in the body enters into this imaginary supply tank, and from there, some of it enters into the rapid compartment, which is the very richly perfused compartment, the medium compartment, which is the medium perfused compartment, and the slow compartment, which is the very poorly perfused compartment. So you have all the carbon dioxide being theoretically emptied into a supply tank, and then they enter into each of these subcompartments. And all of this is controlled. The excretion of the carbon dioxide is controlled by the alveolar ventilation. What is shown here as the drops of waste being emptied. And what is controlling this? The tap here is being controlled by what is called the central chemoreceptors, which are constantly watching the carbon dioxide levels in the chemoreceptors situated in the aorta and the carotid arteries. And they also look at the pH changes and constantly in keeping it at a constant level by either opening up the tap to excrete more carbon dioxide or closing down the tap to reduce the excretion of carbon dioxide, thereby maintaining the amount of carbon dioxide in the blood at a fairly constant level. So this kind of summarizes the CO2 homeostasis. I thought that a lot of my postgraduates who've done PG in the last 25 or 30 years might be attending this APGAP. And for old time's sake, I thought I'll introduce my family. The first slide, or the first two young girls that have come up are my two granddaughters, daughters of my eldest son, Karthik. Karthik is coming up here with his wife, Disha. And this photograph was taken with Anushka, his elder daughter, who's now 7 years plus, and his younger daughter, Amaya, who was about a year old when this picture was taken. Now she's close to 2 years of age. I have a younger son who lives in Bombay, and that's my granddaughter from my younger son, Krishna. Most of my postgraduates in earlier years would have seen Krishna and Karthik attending anesthesia parties at this age at which my granddaughters are right now. And this is my younger son, Krishna, with his wife, Chaitrali, and their daughter, Ananya. Very soon, possibly even before APGAP is over, my fourth grandchild will be born. And I just thought I will leave this blank space here to put up that photograph. Also a picture of me and my wife, who's behind everything that I do. This is what we look like at the present times. And until my fourth grandchild is born, I thought I'll use this empty space to thank Manjunath and Anita, who have been the think tank behind APGAP 2020, and my dear Manipal Anesthesia family, whom I miss very dearly. So we now open up for a few minutes for any questions that might be there. Thank you.